All right, so in this section, which is again section 5.3, what we're going to look at are exponential functions. So it's a new kind of function we haven't seen yet in this course. So what we're going to look at now is an exponential function. Not only are we going to see what it is, we're also going to see what its graph looks like. And now there is a special number that E represents. It is actually very important if you go on into calculus and beyond that. So we will see later on what that number E actually is. And we're also going to see another kind of equation called an exponential equation. Now, let me just review something real quickly. If you have a number A raised to the x, in notation we say A is actually called the base, and the x is what we call the exponent. So in other words, you're raising the base to the exponent. That's what's happening here. Now, also let me go through what we call the laws of exponents. You might have seen these already, these properties, that is, when you have something raised to an integer. And really what the laws of exponents are telling us is they apply to whatever the exponent is. In other words, if you have numbers a and b, a, b, x, and y, these are all numbers. We're assuming, though, a and b are positive. So in other words, what we're assuming is, as you'll see, the base can only be positive. Then we have all these wonderful properties. Again, a lot of these you probably have seen regarding only when the exponents are integers. I know in Math 104, for instance, they teach that, which is, again, college algebra and trig. If you don't remember those, that's okay. You can always ask me for help. I'm more than happy to help you. Let me just point out a few things quickly, though. Here, if you do 1 raised to any exponent, you will get 1, no matter what that exponent is. Also, this one is actually very useful. What this allows us to do is it allows us to solve exponential equations. I mean, we will use this method for solving them. So what this is telling us is, like bases give you equal exponents, and the other way around. So if you have two bases that are equal, the exponents have to be equal as well. That's the laws of exponents. We also have this terminology here. Basically, an exponential function is going to be a function that looks like this. You have some non-zero constant c times a to the x, where the base, we're taking it to be positive. And also it can't be 1. Basically, because if a were 1 raised to anything is 1, and then we really just have a constant function. And a constant function, again, we really just don't want to deal with that right now. And we also, and the c here, the number in front, that's non-zero. That's actually going to be called the initial value. We'll see why later. It's actually just based on this property. And the base, the a, we also call it the growth factor. And that we'll actually see why a little bit later. And there's just notation I wanted to bring up, that if you take something and raise it to the 1/2 power, that notationally is the same as the square root. Okay. So now I figured it's good to do some examples. Suppose a is 2. Then, of course, the exponential function we get is 2 to the x. So I'm just saying here, well, let's evaluate some of this. Okay. So if we do, for instance, f of 1, okay, well, that's just going to be 2 to the 1. And really, any number to the 1 is that number. So in particular, we're just going to get 2. That's all. If we do f of 0, again, this I included as one of the laws of exponents. If you go back to this, If you do f of 0, well, that's just going to be 2 to the 0. So going back to that laws of exponents, this is going to be 1. And f of a half, well, that's just going to be 2 raised to the 1/2. But going back to the notation above, that's the square root of 2. And if you did calculate that, you can approximate it by a decimal. For now, let's just leave it the way it is. And here's another example. Here I'm telling you, or I guess reminding you, so to say, that 3 to the 4th is 81, 2 to the 4th is 16, so we want to calculate this. Okay, well, if you do 3 easy mistake to fix. If you do 3 over 2 raised to the 4th, so here we're going to be using this law of exponent, where if you have a over b to a power, that's a to the power over b to the power. So raising to exponent, so to say, is compatible with the division. So here we're going to have 3 to the 4th divided by 2 to the 4th. And using what's given, sorry, that's a 4, we're going to get 81 over 16. Okay, so that's good. Okay, so let's keep going now. Here's another example. Here we have 4 to the square root of 2 raised to the square root of 2. Now, how do you take a number and raise it to the square root of 2? Well, that's not obvious. I mean, a calculator could do it, but let's forget the calculator for the moment. But what's nice is we don't have to worry about that, because if we go back to our laws of exponents, we can use this property. If you take a base to an exponent, the whole thing to an exponent, that's the same as this over here. So using that, what we're going to have is this. Let me just rewrite it for fun. Raised to the y. That's the same as a to the x times y. So in this case, we're going to multiply exponents. Same thing over here. We have 4 to the square root of 2 raised to the square root of 2. Well, using this property, we have 4 to the square root of 2 times the square root of 2. And of course, that's 4 raised to the 2, since the square root of 2 times itself is just 2, and that's 16. Here's another example. We have 9 to the square root of 12 raised to the square root of 3. So using the same property, we have 9 to the square root of 12 raised to the square root of 3. That's equal to 9 to the square root of 12 times square root of 3. And one of the things about square roots or radicals is that you can multiply them. So we're going to get here the square root of 12 times 3. And 12 times 3 we know is 36. So we're going to get 9 to the square root of 36. And we have seen before 9 to the square root of 36 is 6. So we get 9 to the 6.